Well, it's starting to look like this is all we're going to have today. So I'm going to go ahead and get on with the lecture. I know I'd say I'd wait till 10 after, but there's only 4 of y'all in class today thus far. So I'm going to go ahead and get into this stuff. So the remainder of what we're going to be talking about will be chapters 5 and 6. What this is all going to be about is the idea of the antiderivative and area underneath a curve. So, question, what is an antiderivative? Folks at home, what do y'all think?
What was your question?
What is an antiderivative? What do you think that would be?
I have no idea. The opposite of a derivative.
Yeah, right? The opposite of a derivative. It should be undoing the derivative, whatever that means. So let me ask you. Let's say I told you there was a function, f of x, that the derivative of this thing is equal to 2x plus 1. What do you think the function would be? Given that the derivative of our function is equal to 2x plus 1, what do you think the function would be? What do you think? Not quite. So let me go about it a different way. What's the derivative of x squared plus x minus 6? What's the derivative? Well, let's start with just 1 right now. The derivative of this thing would just be 2x plus 1, right? Now, what's the derivative of x squared plus x plus 12? Well, that would just be 2x plus 1, right? And just for good measure, let's look at one last derivative. The derivative of x squared plus x. Well, that again would just be 2x plus 1. So if I told you there's a function whose derivative is equal to 2x plus 1 and asked the question, what is our function? We've already seen there's 3 different choices here. But notice something, they all have the same form. Whatever our function is, whatever this guy is, it's going to have the form x squared plus x plus some constant. So if we're going to undo the derivative, we somehow need to account for this constant, right? And the reason why is because we have all of these different functions whose derivatives are the exact same, but they only differ by a constant. So to answer this question, I'm going to go ahead and write out, I would write all this. F of x is equal to the antiderivative, that's what this symbol represents, for undoing the derivative, of 2x plus 1 with respect to the differential x. So this dx just tells you what you're taking and undoing the derivative with respect to. This thing is going to be equal to x squared plus x plus a constant. And the reason for this constant is because, well, everything that has this derivative looks like this up to a constant. Make sense what I mean? Now, just to check it, take the derivative of that. Here you're going to get 2x plus 1, and this constant is going to have a derivative of 0. So it still matches, right? And this is what we're going to be talking about throughout this set of material. So just like I asked, we've got some function. We're going to take the derivative of it. But we want to go the other way around. We want to say, I've got a derivative. What's the function? So if we're given the derivative is equal to 2x and asked what is g of x, we're going to undo the derivative, but we need to account for that constant. That's what the point of all of this is going to be. So we've got this example of f of x is equal to 3x, another example of 6x squared plus 3x minus 12. We're asked what their derivatives are. F prime is going to be 3. G prime is going to be 12x plus 3. And that makes sense because derivative here is 3. Derivative here is 12x plus 6. Plus 3. Then we have a couple other examples of another function, 3x plus 5, and then another function, 6x squared plus 3x. We take their derivatives, we get the exact same things again, right? So we see that we have two sets of functions whose derivatives are in fact the same. We have this set, we have this set. And the difference between both sets, between the elements of both sets, is that this is different from this by a constant. This is different from this by a constant, right? Here we're subtracting 12, here we're adding 0. Here we're adding 0, here we're adding 5. So they differ up to a constant. So we have two different functions that give us the same derivative. And as a result, when undoing the derivative, so taking the antiderivative, we would say it's equal to some function plus a constant. Just like what we have up here. Make sense what I mean? So if f of x, the derivative of f of x, of capital F of x, is equal to lowercase f of x, then the integral of f of x with respect to x is going to be equal to capital F of x plus a constant. And the reason why is because we don't know what this thing actually looks like. We just know what it looks like up to a constant. So just some notation, the anatomy of integration, we've got this integral sign, and it's going to tell us you're taking the indefinite integral of something. That's all this means. That I should say that's all this means, is you're integrating f of x with respect to x. This is called the indefinite integral. And a couple, I guess in next lecture, we're going to talk about the definite integral. And the way we evaluate it is we say that the integral of f of x dx is equal to capital F of x plus c, the antiderivative. This is just a differential. This is called the integrand here, and this is called the integral sign. The differential just tells you what you're integrating with respect to. The integrand is what you're integrating, and the integral sign just tells you to integrate. So, given that lowercase f of x is the derivative of f of x, the antiderivative of f of x with respect to x is equal to capital F of x plus a constant. So just as a couple examples, let's say we want to integrate 2 with respect to x. It's going to give us 2x plus a constant. We want to integrate 3x squared with respect to x. Well, undoing this derivative is going to give us x cubed plus a constant. And then again, the integration of 4t with respect to t is going to give us 2 times t squared plus c. Now, just as a way of checking our work, whatever we integrate, the derivative of that thing should be equal to our integrand. So if you integrate a thing, and then you take the derivative of that thing, you should get back what you put through the integral. Make sense? Folks at home, does that make sense?
Yes.
Cool. Now, some basic rules of integration. Let me turn this up really quick so I can make sure I can hear y'all. Oh, y'all cannot see those notes, can you? I apologize about that.
There's a way to like zoom in, like click on, instead of watching like your computer notes, you can make your whiteboard the big screen.
Yeah.
So like on my end, so like I can see yours.
Okay. See, when I recorded, it just had a frozen screen just now, which was weird. Like it just showed the name, like the entry lecture thing. It was weird. But anywho, getting back to the lecture though, we have a couple basic integration rules. And notice these just mirror our derivative rules, right? If we're integrating a constant, well, think about what the derivative of a constant times a function was. We're just undoing that, right? So we're going to get back k times x. That's where this integration of a constant comes from. So it's the reverse of the derivative rule for that. Just to show that again. We've got the derivative of k times x. It's just equal to k, right? Make sense? So this first rule is just undoing our derivative. Similarly, k times a function. That's a constant multiple of a function, right? In reverse. The sum and difference rules are exactly the same as the sum and difference rules for derivatives, which makes sense because if d dx of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x, then it makes sense that when we integrate f of x plus g of x, we're going to have that same rule show up. Similarly with the difference. And now notice for the simple power rule, again, it's just the exact opposite of what the derivative of a simple power is, right? So I'll write that out on the board. We know that the derivative of x to the n plus 1 is equal to 1 over n plus 1 times x to the n. So again, it's just undoing it. But in each of these, and I shouldn't say in each of these, in 1 and 5, we have plus a constant. That's because, again, these things differ up to a constant. Whatever we took the derivative of to get what we're integrating can be different up to a constant. Now, the reason why that constant doesn't show up in 2, 3, and 4 is because we're not actually evaluating the integrand. We're just saying that this integrand or this integral is equal to this integral. Once we get through this, though, we're going to add that c back in. Does that make sense? So just to reiterate, this fifth rule, it's just the reverse of the derivative. Make sense? So why don't we all try to really quickly find C? I'll give you all about 2 minutes to do that. So what do you all think? What's C?
It's gonna be that first rule.
Okay.
The constant rule. And so it would be -5t plus the c.
Exactly. So all three examples are examples of this first rule, the constant rule. So just like was said in here in class, we're going to apply this first rule. We're going to get that the integral of -5 with respect to x is going to be equal to -5x plus a constant. And just to verify all of these, up here we've got A and B. They do in fact agree with what's on the slide. And just like we said with C, it is in fact -5t plus a constant. So what about in this case? Now we've got our x involved. This is going to be the simple power rule for integrals, right? For the indefinite integral. Which told us that the integral of x to the n dx is equal to 1 over n plus 1 times x to the n plus 1. We also have the other rule that k times x, or any function really, that this integral is equal to k times the integral of f of x dx. We're going to use both of these rules to solve this problem now. So we've got the integral of 3x dx. This is equal to 3 times the integral of x dx. That's by what's here in blue. Now we're going to apply what's up there in red to find that this is equal to, my mistake, I forgot, my plus c, didn't I? So this is going to be equal to 3 times the integral of this. We can think of being x to the first power. So we have 1 over 1 plus 1, or 2, times x to the second plus a constant. Now look at what happens. When we distribute this 3 all the way through, we're going to get 3 times a constant, right? Which is just a constant. We don't know what that constant is. So we can think of this as constant number 1. And our result is being 3/2 x squared plus 3 times constant number 1, or 3/2 x squared plus constant number 2. But because we didn't know what C was in the first place, it's arbitrary here. We don't necessarily have to have the 1s and 2s as subscripts. Does that make sense what I mean?
So you just drop the 3 in that second one?
Yeah, because all we're saying is 3 times whatever this thing is equal to some new constant.
Okay.
We don't know what it is, just designate it as your second constant. But because all this is arbitrary, we can go ahead and drop the subscripts themselves, unless we were actually trying to solve for what C1 was. So just to show again what this looks like, we're pulling out that constant 3. We're rewriting x as x to the first power. Then we're integrating. We're saying, hey, just add that constant back in. And because this thing is arbitrary, it doesn't matter if we actually denote it as C1, C2. We can just say C. We don't know what C is. We don't really care in this particular case what C is. Later we might. But for right now, it's just a constant. So the way to go about solving these, take your original integral and rewrite it however you can. Then apply the rules of integration. Then simplify your work as much as you can. Just like what we did here. So their integration is actually 2 different processes, the way we wrote it, the way we wrote it up here on the board. But it's the same idea, right? They're just condensing all of that work into one statement. Okay, what about these now? How are we going to solve these? Well, I argue that in both cases, we're going to use the power rule. I'm going to let y'all work on A, and I'm going to work on B up here on the board really quick. So looking at B really quickly, we start off by rewriting our radical as a power. And we say, all right, we're going to use the power rule of integration. We're going to say here that n is equal to 1/2, because that's the power on our integrand, right? So we come over to the power rule, say, all right, 1/2 plus 1 in that fractional denominator, right? Times x to the 1/2 plus 1 plus a constant. That's the rule. So applying that rule, this is going to come out to be 1/3/2 plus x to the 3/2 plus a constant. We can rewrite that fraction as 2/3 times x to the 3/2 plus a constant. Now, what about a? Does anybody solve a?
Negative 1x squared.
I think you're right. I think. Let me go to the board. So for a, we're going to start off by rewriting it. We have x to the 1 over, or my mistake, the integral of 1 over x cubed integrated with respect to x. This thing is equal to the integral of x to the -3rd power dx. Now, applying our power rule, we're going to say that n is equal to -3, right? I'm just writing this here just so we know what I'm taking advantage of, right? What I'm using. I say, cool. This is going to come out to be 1 over -3 plus 1, x to the -3 plus 1 plus a constant. Right? And just like you said, that reduces down to 1 over -3 plus 1 is -2 times x to the -3 plus 1, again, is -2 plus a constant. And checking our work, we do in fact get those values, right? Now they go ahead and simplify everything in both cases. But notice the work is the exact same. So what about something more complicated? What about something like B? What are we going to do here? Thoughts? Folks at home, what do y'all think we're going to do with B?
With the sum.
Yeah, it's going to be that sum and difference rule, right? Got the dx. We're going to use this rule right here, right? So to solve B, we're saying, cool, this integrand, or this integral, rather, of 3x to the 4th minus 5x squared plus x, all integrated with respect to x, this thing is going to break up. We're going to say this thing is equal to the integral of 3x to the 4th integrated with respect to x minus the integral of 5x squared integrated with respect to x plus the integral of x integrated with respect to x. Now from here, this reduces to just using our power rule, right? So this is going to come out to be 3 over 5 x to the 5th minus, rather plus a constant, right? I'm going to call that constant 1, minus, this is going to come out to be 5 over 3 x cubed plus a constant, and call that constant 2, plus this last integral is going to come out to be 1/2 x squared plus another constant. Now notice we can drop all of these parentheses, right? So let's go ahead and drop all of them. And rearrange it so that all of our constants are at the very end. Here we're going to have 3/5 x to the 5th minus 5/3 x to the 3rd plus 1/2 x to the 2nd plus C1 minus C2 plus C3. Well, I don't like having all of these clumped up like this. So why don't we go ahead and rewrite it as another constant? Why don't we go ahead and rewrite it as 3/5 x to the 5th minus 5/3 x cubed plus 1/2 x squared plus some constant c. And all this constant c is all of these put together.
Can you just make it a bigger C?
I just made it AC.
Oh, okay.
I guess it does kind of look like I made it capital, but just AC.
Okay.
We're just saying it's some constant. Looking at how this breaks up, notice we have first that constant rule that gets applied. Well, first we break everything up into individual integrations, and then we pull out the constants. Then we use the power rules. And here, they just went ahead and clumped all of the constants together. This is going to be something we keep doing over and over and over again. The reason why is because it doesn't make sense to keep these as they are. Just go ahead and say, when we integrate at the very end, we're going to have some constant hanging around. All the constants are going to add together, multiply together, whatever. But you're going to have a constant tacked onto the very end. So might as well just call it one constant. And that's why here they go ahead and just call it C. Well, what about something more complicated? What are we going to do here? Well, here we got the integral of x plus 1 over the square root of x integrated with respect to x. That's everything, right? Well, the first thing we can do here is break up that fraction to get x over the square root of x plus 1 over the square root of x. We're integrating this all with respect to x. Well, let's go ahead and use the sum and difference rule. That way we can break up our integrand to get the integral of x over the square root of x integrated with respect to x plus the integral of 1 over the square root of x integrated with respect to x. So this thing I can rewrite in terms of the power. Let's go ahead and do that. This is all going to come out to be the integral of x times x to the negative 1/2. Let's say x to the first times x to the negative 1/2. Integrated with respect to x plus the integral of x to the negative 1/2 integrated with respect to x. And this thing, that can be reduced, right? I'm just going to use properties of powers. Can be reduced to just x to the 1/2, right? So doing that, this whole integral becomes x to the 1/2 dx plus x to the negative 1/2 dx. using our power rules, this is going to become 2 over 3 x to the 3 over 2 plus 1, or maybe my mistake, plus a constant. And this is going to become plus negative 1 over, my mistake, let's actually expand this out so we can see every step and we go along the way. Here we're going to use a power rule. This is going to be 1 over 1/2 plus 1 times x to the 1/2 plus 1 power, all plus a constant c. And on the other side, n is going to be equal to negative 1/2. So we have 1 over negative 1/2 plus 1, all times x to the negative 1/2 plus 1, all that plus some constant. Right? All I'm using here is power rule and power rule. Now we're going to use that same trick to combine the constants together. Just going to call it C in a second. We're going to reduce all of these individual terms of 1/2 plus 1 or negative 1/2 plus 1. When we do, we get, this is going to become 2 over 3 x to the 3 over 2 power plus, this is going to become 1/2, my mistake, 2 times x to the 1/2 power, all that plus a constant. And that 2 just comes from the fact that we have 1 over 1/2, right? 1/2 in that denominator. So we can simplify it to just 2. Makes sense what I mean? This bad boy right here, this 2, comes from the fact that we have 1 over 1/2. So when we simplify it, it becomes a 2. So checking our work, they do something here. They go ahead and simplify it from here to here. They just pull out that power of 1/2. They factor it out along with 2 over 3 to get this down here. Make sense? Now, what if I told you a little bit more information? What if I told you that the derivative is equal to 3x plus 5, and the function when x is equal to 1 is equal to 9? Now, this lets you do something. What do you think it allows you to do? What do you think this little bit of extra information, our function L1 is equal to 9, tells us? Well, let's check it out. Let's play with all of this. Once I get this 40 grades. Now let's start in this problem with just that first little bit of information. That our function, its derivative is going to be equal to 3x plus 5. So f of x equal to 3x plus 5. This tells us that the derivative of f of x is equal to 3x plus 5. So this tells us then that the antiderivative of 3x plus 5 integrated with respect to x is equal to our function plus a constant, right? So let's go ahead and solve this integral. The integral of 3x plus 5 integrated with respect to x is equal to the integral of 3x integrated with respect to x plus the integral of 5 integrated with respect to x. This is going to come out to be 3 over 2 x squared plus 5x plus a constant. Right? Now, this extra bit of information that f at 1 is equal to 9, it tells us that 3 over 2 times 1 squared plus 5 times 1 plus our constant is equal to 9. Well, simplifying all of this, this is 3 over 2 plus 5 plus our constant is equal to 9. Grouping everything together that we can, we have 3 plus 10 over 2 plus a constant is equal to 9. So that's 13 over 2, right? Let's go ahead and write it as 13 over 2. Subtract it from both sides. But 9 minus 13 over 2 is really just 18 minus 13 over 2, right? Or just going to be 5 over 2. So what we've just done, we just found C. All of this tells us that C is equal to 5 over 2. So our function, we just found f of x is equal to 3 over 2 x squared plus 5x plus the constant we just found was 5 over 2. So with a little bit more information, we were able to solve for that constant. And notice here, I didn't use C1, C2, and then combine. I just went ahead and jumped straight to C. And the reason why is because that's just an unnecessary step. We know we're going to combine all of those constants together. But it didn't really change our final answer, did it? It gave us exactly the same final answer we would have had if we left C1 and C2 as they were, right? So just showing the process here, we start off by integrating that derivative. We say, cool, our function has to be equal up to a constant. Has to be equal to 3x squared over 2 plus 5x up to a constant. When we set x equal to 1 and our function equal to 9, that tells us that our constant has to be equal to 5 over 2. So with a little bit more work, we're able to find, and a little bit more information, we're able to find that constant. So in general, if you're told a set of information like this, that you have some function whose derivative is equal to a thing, and that function at a particular x value is equal to something, it lets you solve for c. Everybody cool with this? So what exactly is c doing here? What do y'all think c is functionally doing for our function? Think about what c does when plotting graphs. When you have a function plus a constant, you take the original function, you just move it up or down, right? You don't change anything else about it, just where it sits up and down. So when we consider, for example, a function like x cubed minus x plus a constant, this is the integration of 3x squared minus 1, integrated with respect to x. What this c is doing is it's telling you you have a whole family of functions that could possibly have the same derivative. And until you know what your data tells you, you don't know what that constant is. You just know that all of those functions are the same up to a constant. Make sense? Because all this plus c does is it just moves your function up and down. Nothing more. It doesn't change your derivative in any real substantive way. It just says you got a function, and if you were to shift it up and down, all those different transformations would lead to a function with the exact same derivative. What matters now is what your data tells you. In this case, if we were told that f of x at 2 is equal to 3, is equal to 4, we can solve our function accordingly. We would find that our solution, our particular function, is this one right here. But without that initial data, it could have been any of those. All of those functions will have the same derivative, but only one of those functions will fit the data that we're given. So, like I say here, we're really just, in a sense, making room for whatever our data needs our function to be. So if we're told that the derivative of our function is equal to 2x minus 2, what's our function possibly going to be? What's the antiderivative of 2x minus 2? Yeah. So what I'm asking is, we're told that f prime of x is equal to 2x minus 2. So this is the derivative of our function, right? This means the integral of 2x minus 2 integrated with respect to x is equal to our function plus a constant. Well, the integral, what is this going to come out to be? Should come out to be what exactly? Should that be x squared? Exactly, plus a constant, right? But then we're told something about the data that this function comes from, or that this derivative is found from. We're told that the data, when x is equal to 1, y is equal to 2. So f at 1 equal to 2 tells us that 1 squared minus 2 times 1 plus c is equal to 2. Working all of this out, we have 1 minus 2 plus a constant. Of this is negative 1 plus a constant, which is going to tell us then that 2 plus 1 is equal to c, or just 3. So now we can go back to our solution for our function and plug in 3 for c. Now check out what we've got. What we're solving for is saying our antiderivative gives us all these different possible functions. But the function we're looking for has this data. So with that, we can solve for c. Starting by integrating that derivative, we get our function up to a constant. Then saying, cool, set your function equal to your initial data, 1, x equal to 1, and y equal to 2. Now solve for c. You do, you get that c is equal to 3. So we can come up to our general solution and say, given our data, our initial conditions, we can solve for the particular solution. So the general solution is, I don't know what my data is telling me. The particular solution is saying, I know what my data is telling me. Cool. So in the past, we've talked a little bit about how velocity and height and distance and acceleration, all of these things interact with one another, right? In this problem, what we've got is someone throwing a ball straight up in the air. That was a ball, not an eraser. Threw it up in the air with exactly an initial velocity of 64 feet per second. So at v, or our velocity at time equal to 0, that's equal to 64 feet per second. Our initial height, we call that h of 0, that's equal to 80 feet. And what physics tells us, like I said, just briefly touched on this in a previous lecture. What physics tells us is that acceleration is equal to 32 feet per second squared, I think it is. Yeah, 32 feet per second. 32 feet per second squared. I haven't memorized the metrics, not in the feet. So all of this gives us some way to start this problem. What we need to know from here is that the derivative of height with respect to time is equal to velocity and the derivative of velocity is equal to acceleration. So we're going to work backwards using this initial data. First thing we're going to do, we're going to solve for our velocity function. We know from this data that the integral of acceleration with respect to time is equal to our velocity function plus a constant, right? And that's because of this right here. Now, we're told that acceleration is equal to 32 feet per second squared. So this is the integral of 32 with respect to t. Well, this thing is just an integration of a constant. So this is going to come out to be 32t plus another constant, right? This is our velocity function. Now the problem tells us that initially, so at time equal to 0, we have a velocity of 64 feet per second squared. Really quickly, I have an error in here. It's supposed to be negative 32. Because it's moving down. And that does actually matter in this case, since we're throwing up against gravity and we're accelerating downwards. So since our initial velocity is positive up, our acceleration must be negative to go down. Does that make sense what I mean? So, mistake on my part, that should have been a negative 32. All right. Now, going back to what I was saying, we know v at time 0, which is equal to negative 32 times 0 plus a constant, that thing's equal to 64 feet per second. Well, that just tells us directly that c is equal to 64, right? So our velocity function then has to be equal to negative 32 times t plus 64.
Why is it positive 64, not negative 64?
Because the initial data is telling us it's 64 feet per second.
Okay.
So we're assuming up is positive, down is negative. In some of these problems, especially the more physics-oriented one, it'll help to draw a picture so you get your signs right. But here we're saying up is positive, down is negative. Which is really sad because I consider laying down to put that positive, but dad jokes aside. Solving the rest of this problem, now we know that height, well, the derivative of height is equal to velocity. So the antiderivative of velocity has to be equal to our height function plus a constant, right? So we know that height plus a constant is equal to the antiderivative of velocity integrated with respect to time. And we know that velocity with respect to time, this thing is equal to negative 32t plus 64, all of this being integrated with respect to time. Well, this is going to come out to be negative 32 over 2 t squared plus 64t plus a constant. I just use the power rules here, right? Power rules and integration of a constant. And we can rewrite this as negative 62. I mean as negative 16. Negative 16 t squared plus 64 t plus a constant. And this tells us something when we plug in our initial data again. Our initial data now tells us that the height at time equal to 0, well, that's negative 16 times 0 squared plus 64 times 0 plus a constant is equal to 80. Well, this is convenient because everything reduces, right? This is 0, this is 0. We just get C is equal to 80. So our height function is equal to negative 16 t squared plus 64 t plus 80. Is everybody cool with that? From here, we can go ahead and solve the rest of this problem. Because we assume the ground is equal to 0, right? So we would set t equal to 5 and compare if t is greater than or less than 0. If it's less than 0, then we hit the ground. Make sense? So what all this does, and something I should note, is they use S to denote height. That's because there are other equations that tell you distance as well in the X direction, not just in the Y direction. So modeling that, I can model it in the Y direction or in the X direction. And because of that ambiguity, we just decide to use S of t to denote where we are in general. I like to use H of t to say height. That's why they're doing this. But nonetheless, the model we just came up with agrees with this model, right? Negative 16t squared plus 64t plus 8. And if we look, what we've got is a model that predicts the height of our ball as a function of time, starting at height 80, being thrown up with an initial velocity of 64 feet per second. We will hit the ground at, it looks like, t equal to 5. And following through, we're told that the first derivative of height at time equal to 0 is equal to 64. So that's our velocity function. And we're told that our initial height is 80. We know that the second derivative of height with respect to time is equal to negative 32. So the velocity, the first derivative of height with respect to time, can be generally written in this form. Plugging in our data, solving everything, we get that our particular solution for velocity is negative 32t plus 64, and we carry on in this way until we get to the particular solution for our height function with respect to time. They go ahead and they say we can factor everything out and solve. If this will flip to the next slide, there we go. Now, for the sake of time, I'm going to go ahead and jump to section 5.2, but first I'm going to let you all take let's take a 5-minute break. So come back at 7:15.